Hello, this is Paul from First Attack. In this video, let's prove Theorem 4.6.6, dimension of subspace of a finite dimensional vector space. If W is the subspace of a finite, so V is a finite dimension. We can simply say the dimension is 3 or 4 or something. And then the first result, so W is also finite. And B, the dimension of W is no more than the dimension of the whole space. C. W equals F equals to the whole space equivalent to the two dimensions are the same. This look is obvious. Okay, so let's give a proof. We can set up the dimension of the whole space V is like a 3. Okay, and the same to prove for other. And the first one, see, we have to prove W is finite dimension means the dimension of W is less than infinity, right? Why? We can use proof by contradiction. If the dimension is infinite, so we can find a contradiction. Okay, this is true. Because the dimension is infinite, therefore any basis we have infinitely vectors. We only need to use the first 4 vector, okay, to get a conclusion. And therefore, by the definition, a basis, so any part of the basis should be linearly independent, right? So this is already a contradiction. Why? Because the dimension is 3. Now we have more than 3 vectors in the set. So this set should be linearly dependent, right? So that's a theorem before we have okay, the theorem 4.6.2a. Okay. Because the dimension of the whole space is 3. Now we have 4 vectors, more than 3, so should be linearly dependent, not linearly independent. So what? So therefore this is wrong, right? So the dimension is less than infinite. That's the first part, and then we look at the second. The dimension of W is no more than the dimension of V. Why? Okay, and this is similar. This is just similar as the proof in the first part, A. Why? We can use a proof by contradiction. Okay, so if W has the dimension more than the dimension of the whole space, so therefore we have a dimension more than 3. So simply say 4. 4 means we have 4 vector in the basis. Okay, it's impossible. Contradicted by the theorem 4.6.2 because 4 vector is more than the dimension 3, therefore should be linearly dependent is not a basis, right? Okay, so leave this for you. And then now we look at the C. W equals F equivalent to the dimension equals each other. Okay, let's see why. This is if and only if we have 2 parts. The first part is easy. Okay, so we look at this. And this means if W equals V, the subspace equals the whole space, the dimension should be equal to each other. Definitely, because W is the same as V. The same set, okay, the same space, so the same dimension. The first, obviously, right? And now the second. This means if the dimension equal to each other, do you think W equals V? Let's say the dimension is 3. Okay, still. Because W has dimension 3, so we should find the 3 vectors in the basis, right? So we set up the basis. So let's say S equals V1, V2, V3 is the basis for W because the dimension is 3, so we should have 3 vectors. We have a theorem before. Okay, so these 3 vectors should be also in the whole space, and the whole space still have a dimension 3. See, 3 vector is a basis for W, therefore is also a basis for V, because the number equal the dimension, and the V1, V2, V3 is linearly independent, right? Okay, so that's by the theorem 4.6.4, we have that result before. And now what do we have? So we have this result. The span of S equals what? The span of S should be equal to W, right? And also the span of S equals V. Because S is a basis for W, S is also a basis for V. See, what do we have? And the same set of vectors span into a same space. Therefore, okay, W equals V. Okay, so this is the proof. That's all. Thank you.